Everyone's been asking the wrong question about China's semiconductor progress. The debate has been about nodes, about whether China can reach 3 nanometers, 2 nanometers, whether they can get ASML machines past the export controls, whether they can match TSMC. That's the conversation. And while everyone's been having it, a Chinese company quietly solved a completely different problem that nobody was focusing on. Not how to make a smaller chip, how to make a chip that does more with the same physical space. Longsys just released a 5 nanometers chip called the WM8500. A 128 terabyte drive with this chip inside can store up to 256 terabytes of actual data. Same physical hardware, same NAND, nothing added. I think this is being covered completely wrong. Everyone's leading with the number, with the 2:1 ratio, with the headline. And almost nobody is talking about what this actually signals about where China is going when the obvious doors are closed. That's what I want to get into today. A common assumption in Western tech analysis is that sanctions are working exactly as intended. China is seen as falling behind on advanced nodes, and without access to the latest lithography tools, many conclude it cannot compete at the frontier. I think that view misses something important. The WM8500 doesn't require 2 nanometers manufacturing or EUV machines. It operates on 5 nanometers, a process technology China can already access today. That's not a small detail. It's the central point. The sanctions narrative makes sense if technological progress depends entirely on shrinking transistors. But that's only one path. Longsys chose another. Instead of chasing the smallest node, it reimagined what a storage controller could do. That kind of progress doesn't depend on EUV access. It depends on engineering talent. And that's an area China has been steadily strengthening for years. Every SSD contains a controller responsible for managing data placement, flash memory operations, error correction, and overall reliability. Those responsibilities have remained largely unchanged for years. The WM8500 expands that role significantly. Longsys describes it as a storage processing unit, or SPU. Instead of simply deciding where data should go, it actively analyzes information before storage and determines how it can be handled more efficiently. Its most important feature is real-time lossless compression performed directly inside the drive. Lossless means nothing is sacrificed. The original file is recovered perfectly, byte for byte. According to Longsys, suitable workloads can achieve average compression ratios near 2:1. In practical terms, 1 physical terabyte can store 2 terabytes of original information. Applied to a 128 terabyte drive, that creates up to 256 terabytes of effective capacity. The most interesting aspect isn't the compression ratio itself. It's where the work happens. The CPU isn't responsible. The GPU isn't responsible. The drive performs the task internally and transparently. That represents a meaningful architectural shift. Storage is no longer just a passive destination for data. It becomes an active participant in managing information. And that kind of innovation doesn't require the world's most advanced manufacturing node. The 256 terabyte headline deserves some context. Not all data compresses equally. Text, source code, and databases often compress extremely well because they contain repetition and predictable structures. Compression algorithms thrive on patterns. Video files are different. Most modern video has already been heavily compressed during encoding, leaving little redundancy behind. Running another compression pass often produces only minimal savings. The same limitation applies to JPEG images and encrypted files. Encryption is specifically designed to make data appear random, and random-looking information offers almost nothing for a compression engine to exploit. As a result, a WM8500 equipped drive won't always behave like a drive with double the capacity. Some workloads may approach the advertised ratio, while others may see much smaller gains. That's simply how compression works. What's important is identifying where the technology delivers the greatest value. Enterprise databases, AI infrastructure, and large-scale analytics environments often contain data types that compress efficiently. These aren't niche workloads. They're among the fastest-growing segments of the storage market. If the WM8500 performs as advertised in those environments, its significance extends well beyond an impressive headline capacity figure. Compression gets most of the attention, but another WM8500 capability may be even more important over the long term. The chip can use SSD storage as an extension of system memory. That matters because modern AI models are enormous. Large language models contain billions of parameters that must remain accessible during inference. Ideally, those parameters sit in RAM, where processors can access them with minimal delay. The challenge is that RAM is both expensive and limited. High-end consumer systems might have 128 or 256 gigabytes available, while advanced AI models can require several terabytes. The usual solution is offloading, where some data remains in memory and the rest is stored on SSDs. The downside is latency. Whenever information must be fetched from storage, the processor waits, and those delays can significantly affect performance. Longsys attempts to solve that problem through intelligent data placement. Frequently accessed information remains in RAM as hot data. Information likely to be needed soon is treated as warm data and positioned strategically. Rarely accessed information stays on storage as cold data. If the system predicts correctly, data arrives before it's requested. Longsys claims this approach can reduce RAM requirements by nearly 40% in some AI workloads. It's important not to overstate those claims. Running a large model locally doesn't automatically mean running it efficiently. We still lack detailed performance metrics, including token generation speed and exact memory allocation behavior. Even so, the demonstration is significant because it shows the concept functioning beyond theory. For anyone following the future of local AI, that distinction is far more important than the marketing headline. What stands out to me is how differently this innovation fits into the broader semiconductor discussion. Most Western analysis focuses on what China cannot do: access EUV systems, manufacture at leading-edge nodes, or match companies like TSMC. Those limitations are real, but they can also create blind spots. They encourage people to view the competition solely through transistor density when innovation can happen elsewhere. This pattern feels familiar. In industries like electric vehicles, solar energy, and batteries, China often succeeded not by building the most advanced version of an existing product, but by combining scale, cost efficiency, and targeted innovation in ways competitors underestimated. I'm not saying the WM8500 will transform storage by itself. I'm saying the approach behind it closely resembles a strategy we've already seen succeed elsewhere. Sanctions create genuine obstacles, but they also create incentives to pursue alternative solutions. Sometimes those alternatives uncover opportunities that unrestricted competitors never considered. That's why developments like the WM8500 matter. They suggest that measuring progress exclusively through process nodes may overlook other forms of technological advancement that can still influence markets and reshape competitive dynamics. We should also be clear about what remains unknown. Nearly all available information comes directly from Longsys. There are no widely accepted third-party benchmarks, no extensive independent reviews, and little real-world deployment data. Important questions remain unanswered. How does performance hold up under sustained workloads? What happens to latency when prediction systems fail and requested data isn't where the processor expects it to be? Another critical question involves reliability. Compression adds complexity to every write operation, which means recovery procedures become more challenging if power is lost at the wrong moment. For consumer devices, that may be acceptable. For enterprise environments where data integrity is essential, it's a much bigger concern. None of these uncertainties invalidate the technology. They simply highlight the difference between a demonstration and proven deployment. The WM8500 isn't the most advanced chip announced this year, and it isn't trying to be. What makes it interesting is that it demonstrates how innovation can emerge without access to the leading manufacturing node. Longsys took a component that had performed essentially the same role for decades and expanded its purpose dramatically. If independent testing validates these claims, the conversation around China's semiconductor capabilities may need updating. Because at that point, the discussion is no longer about making chips that are almost as good as the best available. It's about creating chips that solve problems differently. That's the story that interests me most. Not the 256 terabyte headline, but the thinking behind it. In the next video, we'll examine the one component Longseas doesn't control and why it may determine whether this entire approach can scale. If you enjoyed this breakdown, make sure to subscribe to Chip Wars. Thanks for watching, and I'll see you in the next one.